everybody. Thanks to join us again this week for our seminar cycle, The Research of Our Future. This Friday, we will have Pedro Vinicius Sousa is currently doing his PhD at our institute in collaboration with Department of Engineering Materials. The Pedro project thesis is supervised by our researcher, Ferun Carner, by Emilio Jimenez Piqué from the group of research of the structural integrity and material reliability. This morning, we will have Pedro here to speak about his thesis project on finite element analysis of micropillar compression in hard metal with microplane approach of realistic FIB tomography meshes. Pedro, thank you to be here. You can start whenever you want.
Okay, thank you for having me. As you said, I'm going to be talking about finite element analysis of micropillar compression in hard metal with the microplane approach. And one of the interesting parts is that we are using a realistic FIB tomography meshes. I'm going to explain to you what this is about. So first of all, what is micropillar compression? It's a combination of focused IO-beam technique and nano indentation. So the point here is that with the FIB technique, we can make these very small cylindrical samples of the material you're analyzing. And with the nano indentation technique, you can compress it. And it's interesting because it's a simple test. It's a uniaxial compression. And as you can see by the really good images we can have, it's a very good kind of test to observe very closely the local failure behavior in the microstructure and deformation behavior at the microstructure level. So in this work, we're gonna do micropillar compressions. We're gonna do simulations of micropillar compressions. The 3D meshes, we make them with these with the FIB tomography. We also do them with the FIB tomography. We do take several pictures of a region of the microstructure of interest, and on the computer I do a simple triming just to isolate a cylindrical region, and from these photos, from these trimed photos, we can do the 3D models in a special program. So as you can see, two grades. We're analyzing two grades of the same material. The difference being on the size of the carbides, okay, and the amount of carbides also. So as you can see by the images, the first material has smaller carbides. The carbide is the lighter gray phase, okay. So on the top you can see that the carbides are smaller, and there is more carbides also. And the objective here is to use the microplane approach to capture the local inelastic phenomena, not only due to plasticity, but also due to damage because of cracks. So we are using, to compare the results of the simulations, we took from two different articles data. The first article is this one, Sandoval. It's also from this research group, the CFMA group. So they made micropillar compressions on a grade of very similar composition of the fine grade that I'm using on the simulations. And on the other hand, I'm also comparing the results of the simulations on the coarse grade with other experimental data from a very similar grade. Okay, so the micropillar compression experiments allow us to observe inelastic phenomena very closely. So what are these inelastic phenomena that we see in this specific material? First of all, we see a lot of these cracks propagating in this general, more or less 45 degrees angle, and also 90 degrees angle. Here, again, the direction looks very important for this material. And also the binder, as you can see on the third picture, can deform a lot. This is another thing to take into account. The carbides, this is the fourth picture, is a micropillar compression on a single carbide. So you can see that it can also have some plastic deformation by, as you can see, by the slip bands. And also it's interesting to observe the effect, the toughening effect of the binder that it has on the material. So in this picture of the microstructure after a monotonic test, we can see binder ligaments holding up the microstructure together, trying to hold it. So it has this toughening effect. So these are some of the behavior, the local behaviors that we should be able to also observe in the simulations, because we not only want the simulations to coincide with the stress strain curve calculated from the load displacement, we also want it to be able to, we also want to have a similar qualitative results, okay, in the sense that we also want the same failure mechanisms to happen on the simulation. This is telling us that the models are working. So the method, we use the microplane approach. So what's the microplane approach? First of all, it's a method. It's simply a method to enforce the constitutive relation during the simulations, okay? So how does it work? So let's imagine that we are simulating this sample of material here, on the squared sample of a tungsten carbide. If we are looking at a point, so the microplane approach basically discretizes this point into several directions. And then we are going to enforce our constitutive relation in each of these directions. So the constitutive relations give us the stress out of the strain, or vice versa, depending on what you want to do. But in this case, the microplane approach, we use the strain. We have the current strain tensor at this point, and we want to obtain the stress tensor at this point. So this is the final objective, to obtain the stress tensor at this point. So how do we do this? So we begin with the current strain tensor, and each of these planes, they have these unitary vectors that represent the directions of the plane. So we have three. We have n, which is the normal vector to the plane, and we have m and l, which are the shear vectors. They are the shear directions on the plane. We do something that is called the kinematic constraint, and we calculate the strain vector components at every microplane. So it's a very simple calculation. You're just projecting the strain tensor at each of these planes here that you can see on the image. And now we have strain vector components at every single one of these planes. So remember that this whole thing here is just one point of the material. And then now we can use our constitutive law. We take these strain vector components and we can use them in a constitutive relation and and calculate our stress vector components at each of these planes. So each of these planes will have can have three stress vector components. Okay, and now having this, we apply the principle of virtual work, which is this equation, and then we obtain the stress tensor. The principle of virtual work is interesting because it connects what is happening on every single one of the planes at every single direction that we are observing at this point. So it connects that with the macroscopic stress tensor. The principle of virtual work is simply saying that the work done by the stress vector components at every single one of these planes is equal to the work done by the stress vector with its strain conjugate, work conjugate. So it's relating. So it's watching the stress vector components as traction forces on this portion of material, and it's basically relating the work done by these traction forces with the work done by the stress tensor and its strain conjugate. And that's how we obtain the stress tensor. The advantages of this microplane approach is that it allows us to model a great range of inelastic behavior, not only related with plasticity, but also due to cracking. And due to this multidirectional nature of this approach, we can also observe the effect of the interactions between these inelastic, these cracks, these plastic deformations. And it's also connecting micro with macro scale. So in our case, we have two phases. This material it has two phases. The first phase, which is the carbide, we're going to use model M7. So this model is appropriate for fragile materials because it considers fracture due to tensile, compressive, and shear stresses. And its plastic formulation is based on frictional slip formulation, okay? So this is the model we are going to use for the carbides. And as for the cobalt, because the second phase is the binder, is the cobalt, we use the microplane J2. The J2, which is the second invariant of the deviatory part of the stress tensor, is the same tensor that is used to limit the stress with the von Mises criteria, for instance. It's based on this. It's based on this stress tensor, okay, the J2. So it's a plasticity model based on a yield condition based on the J2 tensor. The yield and fracture conditions are also independently enforced at every single one of those planes that we were looking at before. So they are independently enforced, which means that this also applies to the M7 model, okay? So as they are independently enforced, there is a smooth transition between elastic, plastic, and fracturing damage regimes, which is realistic. There is no sudden change in the behavior of the material of the analyzed point. So the simulations that we did, they looked like this. Okay, the geometry is always the same. I applied a displacement load on the indenter on the top. The micropillar has 6,000 micrometers height and 2,090 diameter on the top and 2,700 diameter on the bottom. So this is a very similar geometry to what we have on the experiments. So that's why these dimensions were chosen. The elements used, they are linear hexahedral elements. And the simulations, they have around 100,000 elements, 130,000 elements. The height, the bottom and top diameters. So this is this inclination that it has, it's called the taper angle, which was chosen 3 degrees because of the experiments to be similar. And the displacement load of 400 is more or less what we have on the data available. And then also I considered a contact friction with the indenter of 0.2. So now, after the simulation, we take the force and displacement, and we calculate the stress strain curve from this micropillar. And then that's what we use to compare with the experiments. So this is what a simulation looks like. Here you can see both phases of the micropillar. The green phase is the carbides, and the white one is the binder, is the cobalt. And now if we look at the maximum principal deformation logarithmic, we can see more clearly where the cracks are propagating on the carbide. This is only the carbide we're watching now, just the carbides separated from the binder. So we see that we see a lot of cracks happening at more or less 45 degrees angle in this case, which is very similar to what we observe in experiments. So what we could say here that the model is capturing really well the general direction of the cracks, and it's also also capturing really well the location, because cracks, they usually appear in interfaces between binder pools. And this is what we are observing on these simulations. Even though we didn't specify to the program any interface, there is no special formulation for the interfaces. We are observing a lot of failure in regions that would be interfaces in the real life. And now we see only the binder deforming, and this is von Mises. Von Mises, visualizing von Mises, because it's a model based on the J2 tensor. Severe plastic deformation on the binder face, which is also true in real life. This is other deformed geometries in the other simulations. We also see here, very interesting here, general direction of 45 degrees on the cracks. Also here, if we look at this here, sometimes we almost see the outline of a carbide just by the deformation field around this model. So this is telling us that although we didn't specify any interface, the simulations are telling us that around carbides, the geometry is critical. There are a lot of sharp corners, and this is where cracks begin. Now, if we take a look at the other, we can have a look at the other grade that we simulated. This one, as you can see, the carbides are bigger. They are green. Now let's see only the carbides deforming. So again, very clearly here we see almost an outline of the carbides, because sharp corners, and the cracks begin here. And also, in this case, most of the deformation that we observe on the coarse grade is due to the plastic deformation of the binder. And as you can see, so this is I forgot to mention, this is a simulation of the load and the unload of a micropillar, okay? So again, it loads, and then it releases. And then now we can record, in every simulation, we recorded the load and the unloading phase. And then we can now compare with the experiments. So this is the data for the fine grade. And if we put the simulated results on top of this, we see this. Okay, so as you can see, it matches really well. The unload and the loading part, we see a bit of deviation here, but this is explained because in simulations the contact on the beginning is perfect. On the other hand, on the experiments, it is never perfect, the contact. So that's why there is a little bit of deviation here. But generally, I think the results are good. It's matching the data well. And also here on the coarse case, we see more variations between simulations, okay? Because this happens simply because this is a coarse, as it is a coarser grade, carbides are bigger, so there is more phase composition variability when you do a micropillar. Sometimes, so these micropillars here on the top, for instance, they had more carbides, and the carbides are much more resistant than the binder. So that's why we see this difference. And then also we could have a look at the simulated average and standard deviation on top of the experiments. Again, it follows it matches well, I think, with the experiments. As conclusions, I think the main conclusion is the two main conclusions is that we could match the data quantitatively, but also when we calibrated our constitutive models, even though the parameters of the models, they cannot be measured directly. So maybe this happens a lot in simulation, but the parameters that we use in our models, they cannot be measured directly, right? In any way, sometimes. But the point is that we can, at the same time, by matching the stress strain curves, and we also can match the observed failure mechanisms, so we can safely say that these simulations, they represent well the experiments. Even though we cannot, the models are well formulated, they are based on what is happening on the material. But what I'm trying to say is that the parameters, some of the parameters are not measured. So, but it doesn't matter because we are also observing the same failure mechanisms that we see on the experiments. We are also observing them on the simulations. So I think that's important to, it's an important point to make. Again, more specifically, if we see point by point here, the first one, yeah, stress strain curves are they match the experimental results. Carbide interface regions, although not specifically defined in the simulations, have sharp edges, which were the main source of cracks in the carbide. This is also was an interesting observation. Model M7 is able to capture the general direction and location of cracks on carbides. As I explained to you, the cracks on carbides are usually 45 degrees because it's sensible to the shear stress. And model M7 can reflect this in the simulations. Model J2 is able to describe severe plastic deformation on the binder, goes through. And also, we observe the toughening effect on the material in the sense that in the simulation, sometimes you see individual carbides that were completely broken maybe, but they are still there because what? Because the binder is still holding them behind. So we observe this in the simulations and also in the experiments. And okay, so thank you. That's all. That was all.
Thank you.
Thank you, Pedro. If
You're
there
welcome.
is somebody in the room who wants to ask a question to Pedro, you can open your microphone and do it. Merced, please.
Hi, thank you. Thank you very much, Pedro, for your presentation and for your work. I think it's impressive for such a short time working on the topic. I wanted, I don't know if you said it and I missed it. The experiments, did you make the experiments or were they performed?
No, they are the experimental data. I put the reference. I forgot to specify the reference at the end. I think if I send you the presentation, I can do it. But they are published. The graphs, the experimental graphs that I used to compare, they are published, and I just took it from the papers to compare.
Okay, good. I don't work in this field, so I mean it's difficult for me to understand when you say that the model fits well or quite well or good. In other fields, I think it would be good to have some kind of parameters or figure of merit or something that would help to know what can be defined as good and what is not so good.
Okay.
That's for one comment. Then I think it's the last or just the one before the last conclusion. You say that the model not only provides quantitatively results, but also qualitative. I think it would be on the other way around, no? Because the first thing is that the general behavior is clearly simulated, but then the specific quantity or value, it's not always exactly what you expect. Or can you
okay?
explain me a bit more this, please?
Yes. Let me clarify something that I think I forgot to mention. The simulations, they don't have the same microstructure of the experiments. So this material have the microstructure is very random. It's never the same, and then we cannot rebuild the micropillar that is already destroyed by the compression. So we are simulating with a different microstructure, but with similar grade, with similar composition. So obviously, what is happening here is that the results are not gonna match exactly because you're simulating on a different microstructure, but you're inside the range that you observe in the experiment. So that's why that's what I tried to show. We are inside the range that we observe experimentally.
Okay.
With
And
the
only maybe for people that are not from the field, I think it would be helpful
yes,
so to have
definitely, yeah.
a bit of range of what you think of tolerance.
Okay,
And the last question or comment, in which field these type of materials or the examples that you are analyzing are being used afterwards?
In which application tungsten carbide is used?
Yes.
So it's used the most easy one is mining tools for mining in general for breaking down rocks. They put bits. They call it drill bits. I think drill bits, and then they put little half spheres of this material on the extreme end of the mining tool, and it's very resistant and in high temperature and for wear also has a lot of wear resistance. They can mine really well with this, and also they can use for cutting tools for metal, I think. Yeah.
Okay. Thank you very much, and congratulations for your work.
Thank you.
I guess now we have a question from Yuri. Please, Yuri.
Yes, thank you. Well, Pedro, first of all, thanks for the interesting seminar. Then I also didn't understand this your last conclusion about qualitative quantitative, but since Mercè has already asked you, have explained. So I have just a few small questions because I'm not from this area. That's why I cannot make really profound questions. But the image of the FIP tomography that you were showing, is it, I didn't catch, is it the same image that you take at the end of the experiment, or you showed a few images from different stages of the experiment?
Do you mean the first images of? Okay, let me put the presentation here with the
yes.
second.
No, during the talk you were comparing from time to time the results of simulations with FIP image.
Okay.
So this is at different stages, or you were showing all the time the last image of the FIP, the last FIP image?
I see. You mean here?
Here or during the talk, yes, or here, for example.
So,
these are from different stages, yes?
no, this was no. I'm sorry.
No?
This was different because we made several simulations. We did
Yes.
6 simulations for each grade that we have available. These are 5 of this is the final geometry, final shape after the simulations of 5 other simulations, and this was the one that I showed first. I didn't put it here because you already saw, but then these ones are the 5 other ones. Yeah, I will clarify.
But and what you are showing now is the result of simulations, yes?
Yes.
And the image taken from the experiment, this what you call FIP image, FIP image,
yes,
these they also correspond to these simulations. Yes, you have a few of them.
I have these images that I used. These are from the articles that I compare. I use them to observe. These are of course they are after the compression. So I'm using them just to see. So just to see what sort of mechanisms we have when we compress the micropillar. So what sort of failure mechanisms we observe. So and then the point being we want to match that on the simulations.
And then in your talk, you, by making this comparison between experiment and simulations, you showed images, but I had an impression that in simulations, the cracks or deformations, areas of deformations always appear in the upper part of this pillar.
Yes.
Whereas in experimental results, they are more or less distributed homogeneously. So that looked like a qualitative difference between.
This is experiments. Do you see that the cracks are on the top?
Yes,
More or less?
well, not all
So-
of them. Also in the lower part, depending on the image. No, or I'm misunderstanding what you are.
Let me expand this image maybe if I. So what's happening here is that so what's happening here is that the micropillar has this imperfect geometry because when they do micropillars, these microscopic pillars, they always try to have to have it perfectly cylindrical. But of course, it's very hard at these scales. So what happens is they always have this small inclination, and here are imperfections caused by the FIP tomography. It's not due to the deformation. There are not cracks. Yes, and then all the deformation and failure and cracks appeared on the top in this case, and it's more or less the same here, right? So we also see this on the top. So this is basically due to the taper angle, and yeah, the simulations I matched the taper angle of the experiments just for the final result to be more similar to the experiments, and then we see more deformation on the top.
I see. So in simulations you only show deformations, where in the image we also see defects of the sample. Yes, that's what you want to say.
On the experiments,
yes,
we observe we observe the cracks on the top,
yes,
and then and these images of the simulations they are telling us that right here the material has failed because the deformation here is really high. It means that there is a crack here on the simulation. So
okay.
yeah.
I see. Okay, no, I understood. And just a last question. You were using, or in this area, I see that you use this FIP tomography with ions, but are other techniques like, for example, X-ray radiography or X-ray tomography is also used to study these deformations and morphology changes and so on for these kind of materials?
Yes, well, the FIP tomography, they use it just to make the micropillars, and then they compress it with the indenter. That's all they. And then, of course, they could use some of these techniques to see the direction of the grains of the tungsten, especially. But in this case, we don't have this information. Was that your question?
No, my question was that this is obtained, as you have explained, with this focused ion beam tomography, with ion beams, probably from accelerators, yes? But also other techniques exist, like, for example, X-ray radiography or tomography. So you get images with X-rays.
Okay.
My question was, do you use, or is this technique also used in the area of material studies you are working in, or
yes.
not?
I actually don't know if they are used for this specific application. What I've seen is that they have, you don't need to use FIP tomography specifically to take these sequential pictures. So the point, what you need to rebuild the microstructure in 3D on the computer is a sequence of images of this microstructure taken from I don't know, it could be tomography, or you could, I have seen a work where they simply polish the microstructure and take pictures, polish again, take another picture. So they do this sequentially, and they obtain a sequence of pictures, and they can rebuild the microstructure in 3D on the computer. If you could do the same with X-ray, I don't see why you could not do this the same.
Well, this I don't know. Okay, thank you very much for the seminar and for the comments.
Okay.
I don't have more questions. Thank you.
No, you're welcome.
I don't know if there is somebody else in the room. Otherwise, I could have the last question. It's just a curiosity. The model you are using for this experiment is the same used in the past research project by Valentino? Or you are approaching it with another methodology, with another model?
I don't know what. I'm sorry. I'm not sure if I know Valentino.
Well, it's just to understand if you are using the same model they were using in the group, or you are trying a new model. Because I assume they are already available model, or you made it by yourself.
No, I didn't make it. It was provided by my supervisor firm. So I suppose it's already being used, especially the one for metal plasticity, the J2 model. This one is, I think it was recently implemented by firm, but the other one, M7 model, it's been available for I think 10 years, I think. But I didn't implement them. I just calibrated them for our material.
Mm-hmm. And are you going to compare the result with other models' result, or?
The idea now would be to maybe improve the model somehow, to try and I don't know, capture another mechanism that we could not until now. For instance, there is the first thing that comes up to my mind is the tungsten carbides. They have directions. They are grains with directions. Okay, so the first thing that comes to my mind is try to do the same, but with considering the directions of the grain. So they are just a little bit anisotropic, but that could be something to try. And what else? Improve a little bit the fracture formulation of the J2 model. The other idea that we could do is do the same for other materials and see if the same approach would work with other materials also of interest. So that would be the future, I think. Just maybe improve the models or make another model myself. Yes, that's another possibility.
And do you have any collaboration to try to get some experimental data to quantitatively compare the result?
We do have a lot
apart from the literature, if you are going to have any collaboration to make new experiment.
So in this department, there is a lot of experimental data available that just waiting to be compared. That's one possibility. We can also do the micropillar compression is a little bit complicated because I think we cannot do it here. But for now, there is no plans for more experimental data because there is just a lot, and I think we're gonna use what we have for now.
Okay, thank you, Pedro. So I think we can close this seminar today. Thank you again for your work and to share it with all of us. It's really nice because you are in a group also a bit far away
Yes.
physically from us, from the diagonal side. So it was
Yes.
really nice to know about your research. And we will meet again in 2 weeks This time we will have Roger Courcol, who is a PhD student, also from the RM group. The Roger talk will be in live, and they will be here at SEI, but we will try to have also a remote connection for the people who cannot be here presentially. And so thank you, have a nice weekend, and see you soon.
Likewise, thank you all.
Bye-bye. Thank you.
Bye. Thank you.
Bye bye.
Goodbye.